there, yeah? Okay. So the first thing we study in differential geometry is space curves, all right? So these are sort of trajectories throughout space that a particle could take that are parameterized as a function of some parameters, for example, t. So a curve may be pictured as a trip taken by a point in motion, right? So you have some point, let's say this point P here. This point is in motion, and it follows some kind of trajectory in space. We want to describe that trajectory mathematically, all right? How do we do that? Any point P in space can be described by what's called a position vector. We're all very familiar with the position vector now. And the position vector takes the form R is equal to x hat, y hat, z hat. And x, y, z are the x, y, z coordinates of point P. So point P has coordinates x, y, and z, right? The x, y, z coordinates of point P. All right? Now, if at any time t, the position vector's components can be found by evaluating these three functions. So now what we do is we take this position vector and we make each of these components a function of some parameter. So now they become functions instead of constants that define a point or variables. But if we can evaluate these three components using these three functions, x of t, y of t, and z of t, then the locus traced out by the tip of the position vector defines a space curve. All right? And there's an animation of that here. We have an XYZ coordinate system in the lower right figure. There is a curve C, which starts from this point and follows some path like this through three-dimensional space. And at each instant t, we can point to different points of this curve, right? So this would be R of t1, for example. All right? Oh, shoot. So you can also picture this as a mapping from a 1D line, a 1D space, say from T1 to T2. This mapping over here to an X, Y, and a Z, this mapping, each of the components of this vector R of T, each of the components depend on T, right? So each point on this 1D interval or 1D line, the one-dimensional line, map through this vector map, this vector, position vector, to this map to points along the curve, R of t, x of t, y of t, and z of t, right? Okay, good. So R of t, the position vector, can be written in the following form if we have each of the components of that position vector parameterized as a function of t. And we can write it in this form as what we'll be using in this lecture, in parentheses, and we list the components that are separated by commas. And then we'll list the interval, the endpoints of the interval of the parameter. All right? So for example, there are a couple of parameterizations that are shown on this slide. First, we have straight line parameterization. This line, which is infinite in three-dimensional space, is parameterized by the position vector R of t. And R of t takes this form for a straight line parameterization. And you'll be using straight line parameterizations. If we have a feed, like a focus of, like a phase center of some kind of feed radiation pattern, then from that point to the geometry that we're calculating the reflection from, there will be a straight line, right? Because it's in free space. So say we have some point source here that's radiating like this. We'll have to parameterize a straight line to the point of reflection and from a curved surface. So we're going to use this parameterization a lot, straight line parameterization. All right? Okay, so this parameterization depends on these two vectors, A and B. A is any point on the line, the position vector to any point on the line. And B is a position, is a tangent vector rather. And T is the parameter. So what it says is, if I start from this position vector A, which points to any point on the line, and I add some scaled version of a tangent vector, say T is equal to 1, and we get that, right? If T is equal to 2, then we might get that. T is equal to 3, then we might get that. So you add these two vectors, you get the R of T, right? So that's how you parameterize a straight line. Or you can parameterize a helix in the following way. R of T is equal to A cosine of T. A sine of t, and bt. These are the x, y, z components as a function of. So this is equal to x of t, y of t, z of t, right? And we notice that the a cosine of t and a sine of t describe the parameterization of a circle, right? And the circle of radius a in the xy plane. But then we add the z component to the position vector. So as a function of time, the z component will be changing. So instead of just looping around in the xy plane, we're actually looping, spiraling upward, right? In the form of a helix. All right. That helix is considered right-handed if b is greater than 0, and left-handed if b is less than 0. All right? Okay. And then conic sections here, we have, I think we went over this last time, but there are two main parameters of a conic section. We have a focus f and a directrix, which is parallel to the x-axis and displaced from it. I guess it doesn't have to be displaced from it. You could probably define it as the x-axis, but it's parallel to the x-axis. And it makes a right angle with the axis of the conic section, all right, which is the z-axis. These 2 points define 2 curves, or 2 lengths. FP, so PF rather, the distance or the length of PF, and the distance LP, or PL rather. So different conic sections are defined. If you satisfy this equation here defines all the different conic sections. So the curve that satisfies this equation is gives you different conic sections. If E is equal to 1, the eccentricity is equal to 1, then you have the distance PL is equal to the distance PF, right? And what does that describe? That describes the properties of a parabola, right? A parabola focuses by taking all rays from the focus to the surface, and then normally to an aperture plane here, right? But you could define the directrix out there if you want. It doesn't have to be behind the conic section. And then these are all the same length. So all such points that satisfy PL equal to PF are admissible, and they trace out a curve. In the case of the eccentricity equal to 1, it traces out a parabola. Okay, here's the parabola in more detail. R of t is 2ft 0 ft squared. Why is the center coordinate equal to 0? Why is y of t equal to 0? It's in the xz plane. Very good. Okay, so one parameterization is like this. R of t is equal to 2ft 0 ft squared. And another parameterization, which is Cartesian, is like this, equal to x squared over 4f. That also describes a parameterization of the same curve, the parabola. And r, which is a polar parameterization, is the radius is a function of the angle, right? This angle psi. And that is 2f into 1 minus cosine psi inversed. All right? R has to be greater than 0 here. And the foci are located at x equal to 0, z equal to f. All right. The parameterization of an ellipse, we have r of t is equal to a cosine of t, 0, and b sine of t. So the difference between the ellipse and the helix, at least in the xy plane, is that the radii are different, right? So we have a major axis and a minor axis. All right, that's the parameterization in terms of these trigonometric functions. In terms of Cartesian parameterization, we have this. And in terms of a polar parameterization, we have this. All right? And we have 2 foci now that are located at z equal to plus or minus f. And f is given by the following expression. We're going to use the circular helix a lot today, and the ellipse. We're going to use that as well. And then the hyperbola, we can find with the following parameterizations. Here's the trigonometric, except now we have hyperbolic sine and hyperbolic cosine. And here is the Cartesian parameterization. Here is the polar parameterization. And the foci are similar, plus and minus f, but now we have a plus sign here rather than the minus sign. And the order, I guess you could invert the order with the plus sign anyway. All right? So the conic sections can all be obtained by intersecting planes with these geometry of 2 cones that are pointed at each other. And if the plane is parallel to the axis of the cones, then you get a hyperbola. If it's orthogonal to the axis of the cones, you get a circle. If it's tilted with respect to the axis of the cones, you get a ellipse. And then if you cut only one of them at a diagonal, you get the hyperbola, or parabola, rather. Okay, very good. Okay, so once we have the curve parameterized, we're able to describe the space curve in three-dimensional space using the parametric form of the equations that describe the position vector. Then we can start to calculate what's called the tangent vector, and then other vectors that will follow, which are the normal and the binormal. But for now, how do we calculate a tangent vector? So for a curve r equal to r of t, so here's r, position vector r, which is a function of t, right? For a curve that's described by that kind of parameterization, the tangent vector at the point r of t at a given point is the velocity vector. And that velocity vector is just given by dr dt. All right? So the definition of a derivative is r of t plus delta of t minus r of t divided by delta of t, right? You know that the derivative of, let's say, df divided by dx, that is equal to the limit as h goes to 0 of f of x plus h minus f of x divided by h, right? So it's the same exact definition, but now for vectors. All right, so r of t plus delta t, we increase the parameterization by a small amount. We calculate the new position vector, this one, right? Then we have a minus r of t, so r of t here at the point of consideration. If you subtract these two vectors, then we flip r of t, so now it points like this, right? And then you do a head to tail roll to calculate the sum, the vector sum. So that necessarily is tangent to the curve, right? All right, good. So it's a tangent vector. It's easy to calculate. All you have to do is differentiate your parameterization with respect to the parameter. Dx dt, dy dt, dz dt. Yeah? Very good. Okay. Now we can calculate what's called the speed of the parameterization. We're going to need to calculate this because we're going to look at curves that have a very special speed, which is unit speed curves. So the speed is the magnitude of the velocity vector, which makes sense, right? Velocity is a vector, its magnitude is always speed. So if you take the magnitude of dr dt, the tangent vector, you get this scalar quantity, which is also a function of which point on the curve you're at, which is indicated by the parameter t. And we just find the magnitude of this vector, which is the square root of dx dt squared, dy dt squared plus dz dt squared. All right? Okay, a curve with v of t equal to 1 for all t. So at all points on the curve, the velocity vector has magnitude equal to 1 or speed equal to 1 is called a unit speed curve. All right, these will be convenient for us to derive what's called the Frenet-Seret apparatus. But it's also difficult to obtain a parameterization, which is unit speed. And we'll look at examples of that. Otherwise, the curve is called an arbitrary speed curve, okay? So the distance traveled by a moving point is the arc length along a curve. So the distance from this point maybe to this point is the arc length along the curve. A differential distance d sigma can be found as d sigma equal to v dt, which is a mechanics equation, right? D sigma equal to v dt is the velocity times the time interval. If the time interval is differential, we multiply by the velocity, we get a differential displacement. And this displacement is along the curve because we're using the velocity vector, which is tangent to the curve, right? The differential displacement along the curve, d sigma. And thus, the arc length of a curve, which is parameterized as r equal to r of t from a referenced instant t naught to a variable instant t, is nothing but, so we call it sigma, which is the arc length. We integrate from t naught to t, and we integrate the velocity vector, the magnitude of it, right? The speed. That comes from here. If you integrate both sides of that, then you'll be able to, you'll pick up the length of the curve, the arc length. All right, so we have this velocity, or this 1D line here, t, and we have an interval from t naught to t, and each point on this interval maps through this map r of t, through the map r of t to some point on the curve, right? So R of t is nothing but a map from a parameter space to a physical space, where the parameter space in this case is a 1D interval, and the physical space is three-dimensional space, right? Okay, so the tangent vector that you calculate at each of these points is always tangent to the curve, right? Very good. Everybody understand that? All right, yeah, this stuff is fun. So let's look at reparameterization. So we want to be able to reparameterize these curves so that they are unit speed. If we're given a parameterization of the curve, can we reparameterize it by performing a change of variables such that the curve is unit speed? All right? So consider the example of the circular helix. Its velocity vector and its speed are found as, we take the first derivative of the parameterization of the helix. Here's the parameterization of the helix. Take its first derivative. Derivative of cosine is negative sine. Then we have derivative of sine is cosine. And then we have derivative of bt is just b, right? So each of these are the functions, x of t, y of t, and z of t, right? So we can see the velocity vector, or the tangent vector. Tangent vector always has, a constant z component, and the xy components change according to these functions. Then we can find the speed v by finding the magnitude of that vector, and what we find is it's the square root of a squared plus b squared, and we're going to call that c. All right? Okay, so if c is not equal to 1, then the helix is an arbitrary speed curve, right? Its arc length we can find then by integrating the magnitude of the velocity vector, or the speed, with respect to dt from 0 to t, right? And what we find is c times t. Okay, knowing the speed of the curve and its arc length, we may define a simple change of variables to t equal to sigma over c, right? So if we replace everywhere in this equation, replace t by sigma divided by c, which is the arc length divided by the speed, then the change of change of position or displacement with respect to time is always normalized to 1 because they're dividing out the speed, right? Then that leads to an equation r equal to r of sigma, which is a unit speed curve. Why? Because sigma is the new variable. T got replaced with sigma. Sigma is now the arc length parameter. And if we divide by the velocity, then it's always unit velocity, right? All right, good. So notice we haven't changed the helix curve itself, rather changed its speed by passing from one parameter to another. Such a process is called reparameterization, all right? For a curve r equal to r of t, the reparameterization as r equal to r of sigma with t equals to t of sigma, see this is the function t equal to t of sigma, describes a unit speed curve. In other words, a unit speed curve is a curve whose arc length is its parameter. So you reparameterize in terms of its arc length, and that becomes a unit speed curve. All right? So let's do an example. So, okay, so I picked an example that is not in the notes that you guys have, which is they use the helix, right? But that one's very easy. We just did that one. So I'm going to give you a different example that's a little more difficult. Consider the ellipse parameterization r equal to a cosine of t, 0 b sine of t. From t going from 0 to pi. So what does that look like? Let's do that first. So here is z, and here is x, right? And let's start at t equals to 0, the left endpoint. If we start at t equals to 0, then we plug in 0 here. What do we get? R of 0 is equal to, cosine of 0 is 1, so we get a, 0. Sine of 0 is 0. So we get this point here, right? This point here is r of 0. Yeah? All right, so now let's choose pi over 2 maybe. And cosine of pi over 2, so let's say r of t is equal to pi over 2. We get a times cosine of pi over 2 is 0, right? And then 0, and then b. So at pi over 2, we're over here, right? So this is a, this is b. And then the last point is r of pi. And that gives us cosine of pi is -1, 0, and sine of pi is 0, right? So it's down here. So this one was r of pi by 2. And then here is r of pi. And this point is negative a, right? What happened there? Okay, so the curve looks like this. It's the right half of an ellipse, right? Okay, so, all right. So now let's calculate the tangent vector at any given point. Say at this point, what is the tangent vector here? The tangent vector. The tangent vector is going to be dr dt, so we have to differentiate this parameterization. And we end up with negative a sine of t, 0 b cosine of t, right? All right. The velocity now is, or sorry, the speed is the derivative or the magnitude of the velocity vector, and that is the square root of a squared sine squared of t plus b squared cosine squared of t, right? Okay. Now to find the arc length, sigma, we have to integrate this quantity against the parameter t. So we plug that in here, dt from t naught to t, for example. For us, it would be from 0 to pi, right? Or if we wanted to calculate the whole arc length, but we're starting from the left endpoint, so this should probably say 0 to t, right? So we can rewrite this expression by dividing, we can rewrite this expression. Let's see, we can rewrite this expression by, wait a minute, I forgot how I did this. So b squared minus a squared. So you can write the sine as 1 minus, okay, so the cosine. If we write the cosine of square root of t, probably have to write that as 1 minus sine squared of t, right? And then you can plug that in and you get it, right? Then just factor out this b squared.
Sine of t, right? Instead of sine of
Yeah, that should be t. Good catch. Good catch. That should be t. All right? Okay, so this particular integral here, so we've rewritten this integrand as this following integrand, and by doing that, we have written it in the form of what's called an incomplete elliptic integral of the second kind, all right? And any integral of this form goes from 0 to some endpoint phi of the integration of the square root of 1 minus k squared sine squared of theta d theta. Any integral of this form has been done before and has been given a special name called the incomplete elliptical integral of the second kind, right? For example, if you were to integrate this t naught to t of, say, sine of t, just ordinary sine of t, you know sine of t because you've seen it so many times, but if you were to actually integrate that, you'd have to numerically compute what the value of sine is, right? That's what the software does. So you wouldn't be afraid of integrating sine, right? Because you've seen it and you're familiar with it, but it's the same thing. It's some name of some table, basically, or a series expansion or whatever that you have to go to evaluate the values, right? This is the same thing. I have to integrate this integrand here. It's been done enough that it's been given a special name called the incomplete elliptic integral of the second kind, and this is tabulated as a table. MATLAB has a function called elliptic e, and you can use their function built in to evaluate it, the same as putting sine there, right? So the notation of the incomplete elliptical integral of the second kind is e of t b squared minus a squared over b squared, where the first argument is the Jacobi's amplitude. That's just the endpoint of integration. The second parameter is called the elliptic modulus, and it has to go between -1 and 1 in order for you to use the elliptic function in MATLAB, elliptic e, or incomplete elliptic integral of the second kind, in order for it to have this form, all right? Remember when you first saw Bessel functions, you thought, oh, that's kind of scary. Really, it was a series solution to a differential equation. And that series, rather than evaluating all the terms of the series and adding them up, was just given a special function name, which was Legendre polynomial, for example, or Bessel polynomial, a Bessel function. And in MATLAB, you just went and you used their Bessel H or Bessel J or Legendre P, right? So same thing here. So what's cool about this, though, is anytime you come across an integral, why do they call it elliptic? Because we're integrating sort of the square root of, or the magnitude of the parameterization of an ellipse, right? So anytime you see an integral like this, you can solve it now. So elliptic E, we're going to use the second form where you specify both phi and m, because that's the incomplete elliptic integral of the second kind. Now, the first kind is not incomplete. Or it's complete, rather. So it's still the second kind, but it's a complete integral. And what that one implies is phi is equal to pi over 2. Don't worry about that. We're using the incomplete, this one. So here's some code over here. And I noticed that it's not, let me see if I can fix that really quick. Hold on one second. Okay, I guess I have to break out of this real quick. I don't know why every time I put code in these PowerPoints, it doesn't fix the, where's the font? Okay, okay. Slideshow from current. All right, anyway, here, clear all, close all. That's just to give a brand new MATLAB session, which is clean and clear. Ellipse parameters, we're choosing A equal to 1, B equal to 2. Oh, sorry. Okay, so yeah, clear all, close all is just to give a brand new MATLAB session. A equal to 1, B equal to 2 are the parameters of the ellipse. And then the elliptic modulus, we have to calculate this parameter, right? B squared minus A squared over B squared. Then we can call, we have to set the Jacobi's amplitude. Here we're going to go all the way to the end of our parameter pi. And then we can calculate sigma, the arc length, as elliptic E multiplied by B of phi and K, right? Where phi and K are like this. So phi is we defined it here. And K, we define elliptic modulus there, right? What do we get? We get 4.8442, which is the arc length of this half ellipse, all right? Okay, so you can use that function. Now, to reparameterize the curve, though, and make it unit speed, we have to do the change of variables, where t is equal to sigma divided by v. Sigma of t is the elliptic integral, incomplete elliptic integral of the second kind, and the velocity is here, right? And then once we have that, we replace t. Everywhere we see t, we replace it by sigma by v, and we get the unit speed parameterization, which is now a function of sigma, the arc length, all right? Okay. Good? All right. Very nice. All right, so now we're gonna derive the Frenet-Seret frame, or the Frenet-Seret apparatus, and what that is along any given curve, we can calculate a moving trihedron. It's a very unique moving trihedron. It's a right-handed coordinate system that contains 3 vectors. One is called the tangent vector, which we already saw, to the curve. The next one is called the normal to the curve. And then if you take the cross product of those two, you get what's called the binormal. So there'll be 3 vectors that we describe at each point along a curve. So for example, here is a helix, which is wrapped around a torus, which is the red curve. And you can see this moving right-handed trihedron moving along the curve, right? And the blue vector is the tangent vector, which we just calculated. So you can see the blue vector is always tangent to the curve, all right? And then the green vector is called the normal. We'll look at that shortly here. And the red vector is called the binormal. So these 3 vectors define a moving right-handed trihedron. All right? Okay, so let's get into it. So for a unit speed curve, the unit tangent vector we already calculated is dr d sigma. All right? And sigma is our new parameter for a unit speed curve. Indicates the direction of turning along the curve. Okay. So we are going to introduce 2 new parameters. One is called the curvature kappa, which measures the rate of turning. And so the tangent vector is the direction of turning. The kappa curvature is the rate of turning. And 2, the torsion tau, which measures the rate of twisting. And we'll define all of those a little more rigorously, all right? So consider the derivative of the unit tangent vector. So we have the unit tangent vector here. So here's x, y, z, right? X, y, and z. Here we have a curve shown in red, and we have the parameterization in terms of its arc length, the position vector r of sigma shown there in black. The velocity vector at, say, this point on the curve is this blue vector, v of sigma, and it is shown tangent to the curve, right? Okay, if we look at the derivative of this tangent vector, the unit tangent vector, with parameter sigma, then if we zoom into this curve, then we have, here's v of sigma. If we increase sigma by delta sigma, for example, then r of sigma is going to point to a new point on the curve, and we can differentiate that r of t plus, or r of sigma plus delta sigma, and we get a new tangent vector. Okay, so that's, the sigma's way too far away, right? They should be nearly parallel. It's a differential displacement. Okay, so here if we zoom in, here's v of sigma, maybe here's v of sigma plus delta sigma. All right, two tangent vectors. If you subtract those by definition of the derivative, then you're going to get a vector in this direction, right? Okay, good. So we're going to define dt d sigma, which is also d2r d sigma squared because t is dr d sigma, as kappa in the direction of n hat. All right, and we're going to find out what direction n hat is. So kappa is the magnitude of this vector, and n hat is its direction. So we call the direction of this vector the normal to the curve. And the normal vector is orthogonal to the tangent vector. And we can prove that by differentiating this expression. T dotted with t hat is equal to 1 for sure. They're both unit vectors. Now let's differentiate with respect to sigma. That's this expression here. And what we get is, so use product rule, right? So dt hat, d sigma dotted with t hat plus t hat dotted with d t hat d sigma is just two of these, right? dt hat d sigma dotted with t hat. But that's equal to 0 because the derivative of the right-hand side is 0, and you divide out the 2. All right? So you get this expression here. And we know dt d sigma is what we define to be kappa into n, right? So we divide out the kappa here, and we get left with t dotted with n, and that has to be equal to 0, right? So that means the dot product of the tangent and the normal is equal to 0. The tangent and the normal are therefore orthogonal. Yeah? Okay, good. There's a lot of this type of thing where you start with some kind of dot product of unit vectors and you differentiate. You're going to see that all through this lecture. All right? In other words, since a curve is constant speed, no acceleration in the direction of travel. So yeah, what does this say? So remember, this is like the acceleration, right? The acceleration must be orthogonal to the velocity because the acceleration is in the direction of the derivative of the velocity. So, okay, think of this. The velocity is here, tangent vector. If we differentiate the velocity one more time, which is the second derivative of position, we get acceleration. So now we're talking about the acceleration of the curve. And the acceleration of the curve we define as kappa into n. And we just said that the tangent, or the velocity, is orthogonal to the normal or the acceleration. So in other words, if a curve is accelerating, but it's maintaining constant velocity or constant speed because it's a unit speed curve, then the acceleration has to be orthogonal to the velocity because you're not changing the kinetic energy, right? You're not changing its speed. So if it's accelerating and it's not changing its speed, then it has to be changing direction only. And therefore, the acceleration and the velocity are orthogonal. Yeah, that's another way to look at that. Okay. All right. Any question? Go ahead.
So the cross product will be the third vector.
Yeah, we're getting to that for sure. What's going on here? Okay. Okay. All right. The magnitude of dt d sigma is the curvature kappa. Kappa is always positive. It's always defined to be positive. As the curvature increases, the turning of the curve becomes sharper, right? Okay, look at it here. If you have this vector here and the next parameter, a delta displacement of the parameter lands you there, if this curve is very, very sharp, then these two vectors, if this curve is very, very sharp, these two vectors will be kind of further apart, right? So that means the vector dt d sigma is going to be longer, which means it'll have a higher magnitude, which means that kappa is increased for a sharper turning curve. If the curve is constant, then here's one parameter, not that, sorry. The tangent would be here, for example, and then sometime later the tangent would be here. You subtract these two, you get 0, right? So there's no curvature. So the sharper the curve is, the sharper the curve, right? The sharper the curve is, the more these tangent vectors are going to differ for small displacements of the parameterization, and then this vector will become longer, and this magnitude will increase. So kappa really is measuring the curvature, right? If the curve is very, very sharp, then the magnitude of the variation of the velocity vector is going to be also large, right? And if it's flat, then these velocity vectors don't change at all, and there's no curvature. So kappa is equal to 0. So measure the curvature of the curve, right? Okay. So, all right. An alternative formula for curvature can be found from the following, right? So we have dt d sigma is the definition of kappa d2r. Okay, so this is a formula that we derived already, right? What we're going to do now is take the dot product of the left-hand side and the right-hand side with itself, right? So we have, it's the same as like squaring both sides, right? So you take the dot product of the left side with d2r d sigma squared and the right side with kappa n hat, all right? Then we have, if we factor out the kappa, then we have n dot with n, which is equal to 1. We get this expression. Then kappa can be explicitly found using the derivatives of the position vector rather than the derivative of the tangent vector, right? The curvature, the scalar part of it, right? The magnitude of the acceleration vector, or dt d sigma. Yeah? Okay. At each point on the curve, we now have defined two orthogonal vectors, that being n and t. The third orthogonal vector to the previous two can be found by taking the cross product. So then we define our third vector, which is called the binormal. All right, these three vectors define the moving trihedron, nbt, along a curve. All right, so here's like a curve, for example, and we'll define all these planes. And at some point here, we have the n and the t and the b. All right, good. All right, so the planes spanned by the n and the b is called the normal plane. These two vectors span a plane. Any two vectors span a plane, right? Any two linearly independent vectors span a plane. So the plane spanned by b and n is normal. The plane spanned by b and t is called the rectifying plane. And the plane spanned by t and n is called the osculating plane, all right, of the curve. All right, we'll use those definitions or the names of those planes later on. Okay, very good. Any questions? All right. Okay. Let's consider the derivative of the binormal now. So the derivative of the binormal, dB d sigma, measures the rate of change of the osculating plane. Why is that? So think of this. We have the osculating plane here, which is this plane that's spanned by t and n, right? So this is the osculating plane here. The normal to that plane is b. So if the osculating plane never changes, if it's always planar at the same surface, the same planar surface, then b will always be constant, right? But if the osculating plane is tilting, then the b vector here is going to start to change. So if we measure the rate of change of the b unit vector with respect to sigma, then we'll also measure the rate of change of the osculating plane. All right? So it looks like this, right? So here we have at some point, okay, let me go through the derivation, then we'll explain this figure down here. So differentiating b dotted with t equal to 0. We know b and t are orthogonal. So differentiating b dotted with t is equal to 0 gives us the following. dB d sigma dotted with t which is equal to negative b hat. Okay, so let's write it out. So we have d by d sigma, b hat dotted with t hat equals to 0. From here, we get db hat d sigma dotted with t hat plus plus b hat dotted with dt hat d sigma is equal to 0, right? Now, from here, we can move one term to the other side, and we get this equality. Yeah? All right. Okay. We know what dt d sigma is because we defined that before. dt d sigma, if we look back here, dt d sigma is kappa n. So we can replace now, here we can replace dt d sigma with kappa and n, and we factored out the kappa, and it looks like we've divided through by the negative sign, and that's equal to 0. Okay, what does that say? That says that dB, all we've calculated that, the conclusion from all of that is that this is equal to 0, which means dB d sigma is orthogonal to t, all right? So that's one thing, dB d sigma is orthogonal to t. Now we're going to differentiate b dot with b equal to 1. What do we get from there? We get dB d sigma dotted with b, and then there's a 2 normally in front of here, but we divided it out, is equal to 0. And that means that dB d sigma is orthogonal to b. So we've found that dB d sigma is orthogonal to t and to b. All right? Thus, dB d sigma is in the direction of n, the only direction left, right? So let's take a look at that. So let's write dB d sigma in the direction of n, but we're going to define its magnitude here as tau, which is going to be called the torsion, and we're going to include a minus sign. Okay. Yeah, I think there should be a minus sign here, but okay. Minus tau n hat, right? Where the torsion tau can either be positive or negative. All right? For a planar curve, b hat of sigma is constant, right? So think about this. For a planar curve, here's the x, y, and z. For a curve that exists only in the xy plane, then we know that the binormal to that curve, because the tangent vector is going to be something like this, right? And the normal is going to point something like that in the plane. So the binormal is going to be like this, right? And the binormal is constant for a planar curve. So if the binormal is constant for a planar curve, then dB d sigma is going to be 0, right? Which means that tau of sigma is 0 for all sigma. Thus, what tau is measuring is the twisting of a curve from a planar one. So the curve, if the whole curve can lie in some plane, it doesn't have to be the xy plane, it could be any plane. If the whole curve is planar, then tau is always going to be 0. But as soon as that curve lifts up out of a plane, then tau will be non-zero. So it measures, the torsion measures the twisting of a curve with respect to a planar curve from a planar one, right? So let's look at this little figure. Here I'm showing the osculating plane, right? So the osculating plane is the one that has t and n in it, right? Which is the planar curve we're talking about. Like down here, this planar curve here has t and n in the plane, in the xy plane. It's the same with the curve. Now, this binormal is the normal to that plane. If the binormal ever changes, then the plane tilts, right? So here we have the osculating plane, for example, is this dark blue one, and it has this binormal, right? Now, if the binormal changes to some new plane, then the osculating plane tilts, right? If it twists or tilts, then dB d sigma measures the difference or the change in these two vectors. dB d sigma we know is orthogonal to b. So it's the vector orthogonal to b that's b plus, or b hat of sigma plus delta sigma minus B of sigma divided by delta sigma, right? As delta sigma goes to 0. So this dB sigma is orthogonal to B, and it's pointed from. This should really probably say B hat of sigma, that one. This one should probably say B hat of sigma plus delta sigma, right? So if there is a change in the binormal, then that means the curve is twisting out of the osculating plane, and therefore the tau, the torsion tau measures the rate of that twisting out of the planar curve. Or not the rate, it measures the amount of twisting from a planar curve, right? Any questions? Okay, good. All right, let's define an explicit expression for tau, because so far all we have is tau as part of a definition of the derivative of the binormal. So let's define an explicit expression for tau to calculate it. So here we have dB sigma is equal to negative tau n. That's the expression we derived, where we introduced the torsion parameter. But now we can say tau is equal to, okay, so what are we doing here? We're taking n dotted on both sides of this expression, right? So if I do dotted n hat and n hat dotted, then this becomes negative tau, but I can move the minus to the other side. So I get minus n hat dotted with dB d sigma, yeah? All right. Well, B we know is defined as t crossed with n, so we can substitute that in. And then n we know is, oh, sorry, we've moved the derivative now. Okay, so from this step to this step, we have dt d sigma, and we have crossed with dn d sigma. No, that's not right. You have to use the product rule in here, right? So yeah, if you use the product rule in there, then you open it up, it'll become this expression here. All right. It's probably exactly like the product rule that we've been using before. Okay, so you get this expression here. All right. We know now that, let's see, what are we substituting in now? N, oh no. So we're introducing kappa now here. My goodness, I think, okay, so we got to go back to these definitions. So dn d sigma, let's go back to where we defined the rate of change of the normal. The rate of change of the normal. So dt d sigma is kappa n. So anywhere we have dt d sigma, we can replace with kappa n. So not there. Where's dn d sigma? We calculated that one. Okay. Did we calculate dn d sigma? dB d sigma we calculate on this slide. And no, I don't think we have, right? Okay, so maybe we need to figure out how we calculate that. All right. So d n d sigma. Okay, so what we see here is we see curvature twice, right? So, and it looks like the n d sigma, we never calculated the n d sigma. We could probably calculate that, right? Okay, we'll come back to the derivation, all right? This is the correct derivation, though. You express it in this form. And I'll, instead of sitting here trying to derive it now, I will, well, next class, we'll start with that. Okay, so, oh, wait a minute. No, okay. Oh, sorry, it's not that complicated. All right, so look here. So here t hat is nothing but dr d sigma, right? For sure. And then we have the cross product of d by d sigma. So dn by d sigma is going to be this 1 over kappa d2r d sigma squared. We've seen that before, right? 1 over, what was the expression? 1 over kappa d2r. So d2r d sigma squared is what? d2r d sigma squared is here, right? So I think we use that expression. We divide both sides by kappa, and we get n, yeah? So from here, we can say n is equal to 1 over kappa d2r d sigma squared, right? So let's go back. So here, so this is t hat for sure, right? Then we have cross product. This whole thing is d by d sigma of, this is n hat from the last slide, right? Okay, now we just have to figure out this one over here. Same thing with n hat. So same thing, right? 1 over kappa d2r d sigma squared, yeah? All right, good. Good. So now we pull out the kappa, make this a kappa squared, and then we reverse the order of this derivative probably. And that gives us, and we can pull out a minus sign, or the cross product. Reverse the order of the cross product, we pull out a minus sign. Let's see what we did here. So dr d sigma dotted with d2r d sigma. And then, oh, it looks like we did a product rule. Yeah, product rule. All right, good. Okay, that's a pretty long expression, right? But if we substitute what kappa is, this is our kappa that we derived before, then we find this expression here, which is a little more manageable. So dr d sigma squared dotted with this expression divided by this. All right, and this whole thing is nothing but kappa. And we had 1 over kappa squared. So it's 1 over kappa squared, rather. All right, very good. So now let's consider dn d sigma. I guess we are going to consider it, but a little bit later than when we needed it. dn d sigma in terms of the moving trihedral components. All right? So dn d sigma, how do we do that? Well, let's calculate the nbt components of this vector dn d sigma. How do we do that? We take dn d sigma and we take the dot product with the n, and we say that's the magnitude of the n component. Take the dot product with b, and that's the magnitude of the b component. Take the magnitude or dot product with t, that's the magnitude of t components, right? Okay. Now, to find this expression, we differentiate n dotted with n equal to 1. That gives you dn d sigma dotted with n is equal to 0. All right? And what that implies is that dn d sigma is orthogonal to n. So what's going to happen to this component? It goes to 0, right? All right, differentiating n dotted with b equal to 0. Why do we do that? Because we need to do that, dn d sigma dotted with b. So we have to differentiate n dotted with b equals to 0. We know those are orthogonal. We get dn d sigma dotted with b is equal to negative n dotted with db d sigma. That comes from the first derivative of this equality. You get this expression as a result. All right? Well, that's equal to negative n dotted with negative tau n, because dB d sigma, we just said, was negative tau into n. All right? Okay, and that gives you tau. Yeah? Good. So this whole thing becomes tau into b. Yeah? All right, what about this one now? dn d sigma dotted with t, we're going to have to differentiate something with n and something with t, right? So what is n dotted with t? Well, that's equal to 0. Let's differentiate it. We get dn d sigma dotted with t is equal to negative n dotted with dt d sigma. And we know what dt d sigma, that's kappa times n. So then we get negative kappa. So what we've done now is we've written dn d sigma in terms of tau and kappa. All right, so it seems like a lot of vector derivative gymnastics that we're doing here, right? But they'll all come together. We're deriving differential equations in order to calculate this moving trihedron, the torsion, and the curvature along any arbitrary curve, all right? That is here. So combining the following results gives a set of equations describing the motion of the moving trihedron along a unit speed curve. So dt d sigma, dB d sigma, and dn d sigma. How do all of these vectors vary along the curve, right? Well, the variation of the tangent vector along the curve is related to the curvature of the curve. We saw that. If the tangent vector varies a lot, if I change a small displacement in sigma, right? Here's sigma, sigma naught, sigma. If I change a small displacement in sigma, so to here, so this is delta sigma, this maps over to, say the curve has a sharp curve, then the tangent vector here is going to be like that. The tangent vector here is going to be like that. So they vary a lot, right? So if this vector, the rate of change of the tangent vector is large, then the curvature must be large, right? That's what that implies. So that's why the magnitude of this derivative is equal to kappa times n. All right, and then we said the binormal. The binormal sticks orthogonal to the plane of the tangent and the normal. So if the binormal is varying, then the curve is twisting from a planar one, right? If the curve always stays planar, no matter where it goes, if my hand is the binormal, then it always stays in the same direction as constant. The curve is planar. But if the binormal starts to change, then the plane which is orthogonal to the binormal starts to vary, and the curve starts to lift up out of the plane spanned by the normal and the tangent. All right? So the torsion describes that. And then we just calculated that the n d sigma, the rate of change of the normal, is related to tau and kappa. All right? Good. The above are called the Frenet formulas or Frenet-Seret formulas. So ta-da, we've gotten there. These are the three equations that we needed to calculate the Frenet formulas, right? These are the Frenet formulas, Frenet-Seret formulas, which are independently derived by both Frenet and Serret around 1850. Okay? All right, so in summary, there are 5 important quantities to compute at each point sigma on a unit speed curve r, which is equal to r of sigma. That is the moving trihedron, n, b, and t. So here's how we calculate that. For any given curve that we have parameterized like this, we can calculate first the tangent vector by differentiating that, yeah? Then we calculate the derivative of this tangent vector. So we calculate the tangent vector first by differentiating the position vector. Then we differentiate that tangent vector we just calculated. And that's equal to kappa times the normal. And then we find the third vector by taking the cross product of the previous two. All right? And then the curvature is found with this that we derived, and the torsion is found in this way, right? And the variation of NBT along the curve are described by these differential equations, which describe the variation of the unit of the 3 vectors, the moving trihedron along the curve. Yeah? Okay, let's do an example. So, as we previously noted, the helix has a unit speed parameterization of r of sigma, which is equal to a cosine sigma divided by c. So we replace t with sigma divided by c. We divided out its velocity, which in this case, the helix has a constant velocity around the curve, but normally the velocity is a function of the parameterization, right? The parameter t, or the, in this case, the parameter, it won't be a function of the parameter sigma, right? So it's a unit speed curve. So anyway, we divide by the velocity, which is the same for all points on the curve. We get a cosine sigma by c, a sine sigma by c, and b sigma by c, where c is equal to the square root of a squared plus b squared, and a has to be greater than 0. All right, so the unit tangent and its derivative we find by differentiating first. The tangent is found by dr d sigma, so we differentiate that. The derivative of cosine is negative sine. The derivative of cosine is sine, or derivative of sine is cosine rather, and then we get b over c, because differentiating with respect to sigma. Yeah? Okay. Now we need to calculate dt d sigma, which is d2r d sigma squared. And that is the second derivative of r, basically. And we get this expression here. All right. Now we calculate the normal. So we need to calculate the normal, which is okay, first off, we need to calculate, to find the normal, one part of that is to calculate kappa, the curvature, which is the magnitude of dt d sigma. And if you take the magnitude of this vector, you get, so the magnitude of that is, the square root of a squared divided by c to the 4th cosine squared of sigma divided by c plus a squared divided by c to the 4th sine squared of sigma divided by c. And if you factor out this a squared, so you get a divided by c squared into the square root of cosine squared sigma divided by c plus sine squared sigma divided by c, and that's equal to 1. All right, so this is all equal to a over c squared. Okay, so that's that, yeah? Now, we calculate the normal now by taking the unit part of this, right? Because this was equal to kappa times n hat, right? So first we calculate the magnitude of this vector, that's kappa. Then we factor that out. Whatever's remaining is the n hat. right? So n hat is the unit vector of dt d sigma, which is negative cosine sigma over c, negative sine sigma over c, right? If I multiply a squared over c squared times n hat, then I get back this vector here, the dt d sigma. Okay, so what does that say? That says that n hat points radially inward toward the axis of the helix. Okay, so that's because it's negative and negative, and it points toward the origin then, because normally cosine of sigma over c, sine sigma over c is the parameterization of a circle, right? And the position vector starts from the origin and goes to the curve, but it's negated, so now it starts from the curve, goes to the origin at all points, right? And we can see that here in this animation. In that animation, we have the blue one is the tangent, right? The red one is kappa times n hat, or dt d sigma, the derivative of the tangent vector, the blue one, with respect to the parameter of the curve. Okay, the binormal, now that we have n and t, we just find b by doing the cross product. And if you calculate the cross product, you get this expression. And that is this sort of green curve, the green arrow. The one that's vertical, right? So let me ask you a question. Does this green vector vary? Why? What's that? The green vector is the vertical one. Does it vary?
No.
It doesn't? Remember what the variation of the green vector, the variation of the binormal, what does that measure? Twisting of the curve with respect to planar curve. This curve is not planar, right? It's three-dimensional. So that means that the binormal must vary, and it varies exactly as the amount of torsion, right? Okay, good. We can calculate that right here. So dB d sigma is the variation of the binormal with respect to the parameter of the curve. And we get, so we have the binormal here. Now we just differentiate this with respect to sigma, and we get this following expression, all right? Well, now we can find, remember dB d sigma, its magnitude, dB d sigma, its magnitude is tau, and its direction is normal, right? So let's go back here. So the magnitude of dB d sigma is b over c squared. So it has torsion. It's not a planar curve, it has to. Okay, good. All right, so that's for arbitrary speed or unit speed curves, right? So we have to find a special parameterization where the curve is parameterized as unit speed with respect to its arc length. But that's very difficult to do a lot of times. So it'd be better if we came up with formulas to calculate all of these quantities, the NBT and the kappa and tau, for an arbitrary speed curve, which is a parameterization that you would initially come up with, something you could write down really easily, right? So let's derive the formulas for arbitrary speed curves. All right, for an arbitrary speed curve, the speed is found in the same way, the magnitude of the velocity vector, or dr dt. So we get this expression, the square root of dx by dt squared plus dy by dt squared plus dz by dt squared, right? Okay, let's employ the chain rule to write the derivatives of r of t as the derivative. Okay, so the derivative of r of t here is equal to, let's introduce the parameter d sigma, or sigma rather. So d sigma dt multiplied by dr of sigma d sigma. If these two cancel, which you're not supposed to do, but if it does, then you get back to dr by dt, right? Okay, so d sigma dt, we're going to call the velocity, right? So d sigma dt is the, remember, what is the velocity? It's the change in displacement with respect to the change in time, right? Or the parameter in this case. So d sigma is a displacement of arc length along the curve, a differential arc length, and dt is a differential change in the parameter, or in this case, we can think of it as time. So this is the change in, is meters per second, right? This is the velocity. Okay, so dr d sigma is equal to v times t. Oh my goodness. All right, so dr d sigma is equal to v times t, right? So what does this say? If this was a unit speed curve, what would the right-hand side be? Just t hat, right? So if you go here, let's look at where we defined t hat was just dr d sigma because it was unit speed, right? The velocity was equal to 1. Now we've generalized it to where dr dt is velocity times t, where the velocity can be different than 1, right? Okay, good. Let's get the second derivative now. So we need to differentiate this. So d2r of t divided by dt squared is equal to d by dt into vt, because vt is equal to dr dt. Then we can use the product rule here. So dv dt into t hat plus v into dt dt hat. And that's equal to dv into dt t hat. That term stays the same. But now we're going to introduce what dt by dt is. Okay, dt hat by dt, which is, we're going to use chain rule here, right? So we're going to introduce d sigma. So d sigma by dt multiplied by dt hat divided by d sigma. And we still have the velocity there. Okay, so now we have dv dt, t hat. That first term stays the same. And we have d sigma dt again, which we know is the velocity. So we get v squared, and then dt d sigma we know already as kappa times n hat. dt d sigma, remember we calculated that back here. dt d sigma is kappa times n hat. So we go back here, and we see that dt d sigma, this is kappa times n hat, and this is v. So we get v squared kappa n hat. All right. So then we can do straightforward manipulation, leads to the following formulas for an arbitrary speed curve, okay? N of t is equal, now it's parameterized with respect to t, not sigma. N of t is b cross with t, same formula as before, except now we have the binormal is found as r prime cross with r double prime, and then you normalize it to make it unit vector. All right? Then the tangent vector is nothing but r prime divided by the magnitude of r prime. So this is the unit vector tangent. dr dt gives us the tangent vector, but it's not a unit vector, right? So now we want to take r prime, which is this is r prime, right? So this is r prime. This is r double prime. Take r prime divided by its magnitude, you get t hat. All right, and then you can find the curvature as r prime cross r double prime divided by magnitude of r prime cubed. And you can find the torsion in this formula, r prime cross with r double prime dotted with r triple prime divided by r prime cross with r double prime magnitude squared. All right, so these are much easier to use. These are what you're going to use in practice. So these all these formulas give you everything you need about the curve. So in your homework, you're probably going to give some geometry. You have to parameterize it and then calculate all of these quantities and analyze the curve, right? Okay, very cool. So let's do a quick example. Consider the arbitrary speed curve parameterization of the helix. Now we're going to make it even faster, right? T is going to go to t squared. So for every little displacement in t, we're going to get t squared of the original parameterization. We're going to make it even faster now, right? So now it's r of t is a cosine t squared, a sine t squared, and bt squared. So it's the same curve, except now it's going to zip along it faster, right? It's going to have a larger velocity. Still c is a squared of a squared plus b squared, and a is greater than 0. The first three derivatives we need for our formulas, right? Our formulas are here. We need third derivative, second derivative, first derivative. We need all three of them. So let's get those three derivatives. R prime is, so we differentiate this cosine of t squared. We get negative 2at sine t squared, and then 2at cosine t squared and 2pt, yeah? Then we got to differentiate that again, and a third time. We get all three of these. Okay? All right. Now we can find the Frenet-Seret frame, curvature, and torsion using the formulas we just had on the last slide. So n of t we find as, okay, so b cross t. So we got to do the other ones first. B of t. B of t is r prime cross with r double prime, and then we normalize it. So r prime cross with r double prime, and we normalize it, we get this expression here. All right. Then, whoops, r triple, or tau. R prime divided by its magnitude. So t rather, not tau, t. You take r prime here, and you divide it by its own magnitude, you get this expression here. All right. And then we get kappa and tau. So if we compare this to our previous example here, where we did everything in terms of sigma, remember for sigma, we found a over c squared for kappa and b over c squared for tau. And look here, we find the same thing, right? And then we look back at the curve. We had parameterization. T hat was negative a over c sine of sigma over c. But here we have negative a over c sine t squared, right? And we know that sigma is equal to ct squared by definition of what sigma is, right? The arc length is equal to ct squared. The above results are exactly the same as the unit speed curve. We get the same exact results if you make the change of variables back to unit speed. What does that mean? That means that the Frenet apparatus depends on the shape of the curve in space and not on its speed. So the torsion and the curvature depend only on the shape of the curve, not on the speed of the parameterization. In other words, reparameterization does not affect the Frenet apparatus. And you get the same NBT, right? It shouldn't be dependent on the choice of parameterization. Okay. All right, so yeah, so we have to get through, all this differential geometry of curves. We're going to do surfaces next, and we're going to define the normals, the principal normals, the Gaussian curvature, mean curvature, how to parameterize a surface, the tangent vectors locally to that surface. And then we're going to define a curvature matrix. The curvature matrix is critical for us to be able to solve Maxwell's equations in the guise of differential geometry and the formulas of geometrical optics. They're all going to be dependent on this curvature matrix. So that's one key parameter we need to get to. And we'll get to that probably next lecture. All right, so we'll do surfaces next. Once we get past surfaces and we did the curves, then we'll launch into the actual geometrical optics derivations, and then we'll get to the geometric theory of diffraction. But it's all of the stuff we're going to do to solve scattering problems now are going to depend on this differential geometry, description of these curves that are defining sharp edges or corners and things, and surfaces that are curved, how to calculate reflection from those, and calculate scattering from these objects, right? All right? Okay, good. All right, see you.